Hello, thank you so much for tuning into my YouTube channel. Today's video is going to be a tutorial on PCA using SVD or Singular Value Decomposition, and I'm going to do it in Python. Let's get started. As I said in this video, I want to talk about principal component analysis using Singular Value Decomposition or SVD. Principal component analysis is a widely used dimensionality reduction technique that transforms high-dimensional data into a lower-dimensional space by capturing the most significant features or principal components, or short PCs. PCA is commonly used to reduce the complexity of datasets while retaining as much variance or information as possible. In a sense, PCA finds new axes or principal components along which the variance of the data is maximized. These axes are orthogonal or perpendicular, ensuring that the principal components are uncorrelated. There are multiple ways to extract principal components. One of them is based on eigenvalue decomposition. Eigenvalue decomposition is a traditional approach where the covariance matrix of the data is first computed. Eigenvalue decomposition is then applied to the covariance matrix, yielding the eigenvectors or principal components and the corresponding eigenvalues, or variance explained by each component. Here is the mathematical equation for eigenvalue decomposition, where C is the covariance matrix of the data, and this matrix right here is the diagonal matrix of eigenvalues, and V is the matrix of eigenvectors or principal components. The second method to extract principal component is called singular value decomposition or SVD. Singular value decomposition is a more efficient method for PCA, especially for large datasets. SVD decomposes the data matrix directly without needing to compute the covariance matrix. This makes it more numerically stable and faster for large-scale data. It also works better when the data matrix is not square, for example when the number of features exceeds the number of samples. The mathematical equation for SVD is given as shown here, where X is the original data matrix. The rows of X are samples and the columns are features. U, on the other hand, contains the left singular vectors. This is related to the principal components. Sigma is a diagonal matrix of singular values. This is also related to the variance explained by each component. And eventually V contains the right singular vectors or principal component directions. In PCA, the matrix V contains the principal components and the singular values in sigma indicate how much variance is captured by each component. SVD is usually preferred for PCA, and there are a few reasons for that. The first one is numerical stability. SVD is less prone to numerical instability caused by rounding errors, especially when working with large datasets. The second reason is direct decomposition. Unlike eigenvalue decomposition, which requires computing the covariance matrix first, SVD can be applied directly to the data matrix, making it more efficient. And the third reason is better for non-square matrices. Eigenvalue decomposition works on square matrices like the covariance matrix, which is sometimes not ideal. SVD can handle cases where the number of features is greater than the number of samples or vice versa. PCA can also be used as a powerful compression tool. When performing PCA, we reduce the number of features or dimensions while retaining the most important aspects of the data, which are captured by the principal components. The general idea behind PCA compression is that most of the variance in the data can often be captured by a small number of principal components, meaning that we can reconstruct the data with fewer components while retaining most of its original structure. There are a few steps in PCA compression. First is dimensionality reduction, second is projection, and then the third is reconstruction. In dimensionality reduction, instead of retaining all the principal components, we can select the top k components that explain the most variance. The higher the variance explained by a component, the more significant it is for reconstructing the original data. Now for projection, once we have the top k components, we project the original data onto these components, reducing its dimensionality. And in the last stage, reconstruction, the compressed data can be reconstructed back to the original space using the selected principal components. Although the reconstruction may not be perfect, a significant amount of the original data structure can be recovered. The mathematical formulation for compression is given as shown here. Given the original data matrix X, PCA decomposes it as shown here. To compress the data, we select only the first k components of V and use the corresponding singular values in sigma. The compressed data is shown as here. This reduces the size of the data while still retaining a significant portion of the variance. The quality of the reconstruction can be measured by comparing the original data and the reconstructed data using an error metric like mean squared error. As more principal components are used, the reconstruction error decreases because more information is included in the reconstruction. However, after a certain number of components, the gain in accuracy becomes minimal, as most of the variance is already captured by the leading components. PCA is therefore ideal for both dimensionality reduction and data compression. Let's go to Python and show you how we can apply all these to a hyperspectral image in NV format. So here's the code. We first import the necessary libraries, and this is where our hyperspectral data is located. The data is in NV format, as I said. And then we're going to load it, and I'm going to be excluding the last band because in my data the last band contains NaN. So you might not have to do this, but I did it because my data contains NaN in the last band. And then we're going to reshape the data into a 2D matrix, and then here we're centering the data by subtracting the mean of each band. And now we're going to apply PCA using SVD, and I'm going to use the first 6 components. You could use more because we have 151 bands. We would have 151 principal components, and this is where I'm going to be showing the first 6 principal components as an image, and then I'm going to be also doing some compression and reconstruction. This is the function that does the reconstruction. There's some explanation here for you. So as you can see, we received the reduced data and then we reconstruct it. And then I'm going to be also showing you the reconstruction error, which is done in mean squared error. And I'm going to be showing the error as we add more principal components, up to 6 principal components. Let's run it and see what happens. So as you can see, my data has NaN, but I already excluded it. Okay, the run is complete. This is the first 6 principal components for my hyperspectral data. And just so you know what my data is, this is my data. This is the sRGB rendering of my hyperspectral data. And these are the 6 first principal components. And then in the next graph, I'm reporting the reconstruction error versus the number of principal components. And you could see that the reconstruction error has gone down as I added more principal components, which makes sense. So you could see that with 5 or 4 principal components, I could capture the whole variance in my data. And you could also access the code using a link in the description section of this video. And that's about it. Thank you so much for watching this video. I hope you liked it and you were able to get something out of it. If you liked it, I would appreciate it if you could subscribe to my channel and also share the video with your friends. Thank you so much and have a nice day.